Hello, my name is Naomi Morris. This summer I was advised by Dr. Henny Admoni and Reed Simmons of the HARP and Razzle Labs, and I was mentored by Michelle Zhao. Today I'll be presenting on teaching humans collaborative policies via demonstration. To motivate the problem, we'll set it first in context. Human-robot collaborations may require the robot to communicate with human partners. So generally, we may have situations where a human and robot are working closely and they may interact with the same set of items or have similar constraints. And so there can be the situation where the robot has a better understanding or context about the task. Imagine a factory where one robot seems to have the same job, but often human partners are exchanged out and have to learn the context of the task. So in this case, the human partner is more of a novice than the robot. And so the robot has particular constraints that need to be communicated to the human in order to collaborate effectively. Our goal is to create a natural pathway for humans and robots to communicate their preferences or constraints with a focus on communicating the joint policy. For our purposes, the environment will be formulated with a human-robot dyad collaborating on a pick-and-place task, where the joint policy is defined by each agent's distinct action. We also define a joint demonstration as a sequence of actions taken by the human or robot. Achieving our goal will require two phases. First, in the communication phase, the expert robot will select a set of joint demonstrations to share with the human partner before any collaboration begins. Next, in the evaluation phase, the human uses the information gained to perform the task interactively with the robot. This sequence of events forms our motivating question. Can a robot teach a human joint policies via demonstration? We believe choosing collaborative demonstrations as a means of communicating underlying reward values may lead to learning or executing the optimal joint policy by the human and robot partners. Our approach begins with the set cover optimal machine teaching algorithm. It was originally formulated for teaching robot agents in optimal policy. Much like our robot expert, it begins with a known optimal policy and environment. In our case, our environment involves two objects, the duck and Lego, with distinct rewards for each agent. From there, we'll build a minimal set of reward functions that result in overlapping policy behaviors, also known as behavior equivalence classes. This is where the reward functions generated will result in a similar behavior as the originally known policy. The space of these classes is dimensionally correlated to the reward function. The image in the upper left is a visualization of a three-dimensional set of overlapping classes. In our case, we have two object types, each with distinct reward values for each agent. Adding the step cost along, we build a behavior equivalence class space in 5 dimensions. The size of the area in this overlapping region defines the informativeness associated with a particular demonstration. From this, we are able to sample demonstrations that we can apply to the human learner. Because humans are different than robots, it may be potentially overwhelming to supply them with demonstrations directly from the machine teaching algorithm. They may infer different information from demonstrations differently. Because of this, we categorize different demonstrations based on the number of objects per object type permitted in the demonstration. This allows us to maintain a Pareto optimal between demonstration simplicity and informativeness. Let's look at an example. In this set of demonstrations, a maximum of 2 objects per object type is allowed. A higher length of teaching sets here is associated with a higher level of simplicity for each individual demonstration. The human should be able to infer that the robot prefers ducks and the human prefers Legos. Additionally, the human can see that it is not costly to help the robot with Legos and save on time steps. In this example, up to 4 objects are allowed per object type. The human learner should be able to infer the same things as before. However, they are only given a single demonstration in the teaching set, making it less simple than the previous example. This organization motivates our second question. What kinds of demonstrations work best for human partners? We believe that categorizing the kinds of demonstrations, by simplicity in this case, can be helpful for understanding the best way to tailor teaching to humans. To explore these together, we designed a general study that would involve real human participants. In the beginning, we generate collaborative demonstrations from the machine teaching algorithm, and then we categorize simplicity level according to the number of time steps or the length of the teaching set, and directly correlate it with the number of objects per type. From there, the robot teacher can share their task knowledge through demonstrations in a visual format, leveled easy, medium, or hard, or through an explicit reward explanation. After that, performance evaluations and experiential evaluations will be collected to get an understanding of how well the human partner has learned. When it's time to teach our human, we put them in the setting of a collaborative cleanup task. In this case, a bunch of objects are strewn across a table, and each agent is able to pick them up and place them in a tray. There are 2 ways that we enact the teaching phase. Visual demonstrations, shown in the upper right here, where each agent is shown to pick up their preferred item, or through explicit reward explanations shown in the lower right, where the human learner must infer the strategy only from the numerical values associated with each object. After each interaction, several subjective measures were taken in the following categories. Fluency, meaning how well the human and robot really work together. Communication, how well the communication method felt natural for the human partner. Learning, whether or not the human partner felt like they learned from the task. And application, whether or not the explanations provided were applicable to the interactive task. On the other end, we have performance-based metrics, which are strictly based on the scores achieved by the human and robot partners compared to the optimal performance. Thus far, we've been able to pilot the study and produce preliminary results. Within subjective queries, easy teaching sets seem to produce the most confident responses above the typical explicit reward explanation. Further analysis on performance data will be produced and communicated in the future. To further extend this work, a robot partner with more expertise should be able to adaptively explain the team's policies to a human less acclimated to the task domain. This means that in a full loop, a robot may be able to adjust its demonstrations or explanations to the human partner's learning needs. This concludes my presentation. Thank you for watching.